Well, thanks for joining. My name is MacKie. I'm an assistant professor at the University of Florida in geology. And I am interested in glaciers and ice sheets, specifically the conditions underneath the ice, including the topography. So I'm going to share some of my work on simulating the subglacial or bed topography of the Greenland ice sheet and our work to accelerate those algorithms that we've been developing throughout the UF NVIDIA GPU hackathon. And I also want to thank my undergrads, Matt Hibbs, Caroline Riggle, who worked with me in the hackathon, and our hackathon mentors, Nick Tyler, Eric Stubbs, and Vineeth Gutta. So I'm going to share a little bit of background on why we want to map the topography underneath the ice, some of our approaches to GPU acceleration that we worked on during the hackathon, and then some of our ongoing work to improve the simulation speed of these algorithms. So the topography underneath glaciers is a primary control on ice sheet movement. So it's one of the most important parameters we need to map when we're making ice sheet models and sea level rise projections, because it controls the motion of the ice over the landscape. We can measure topography from airborne ice penetrating radar. So there are millions of line kilometers of flight lines across the Greenland and Antarctic ice sheet that give us bed elevation measurements. But there are large gaps in these surveys, and they have to be interpolated somehow to create continuous maps that we use in ice sheet models. Conventional approaches to interpolating these line measurements are deterministic, so they're designed to optimize accuracy. This is an example of ice-free land, where I pulled out some lines to represent a radar survey, and then I applied a more traditional interpolation method to these lines, and this is what we get. So this is the kind of information that we use in ice sheet models, even if the real topography looks something like this. And the problem is that we lose a lot of the texture in the topography. So ice is going to flow differently over a smooth surface than something more realistic. And the other issue is that we're not accounting for uncertainty in the topography when we're just using something like this. So what we do instead is we do stochastic modeling or geostatistical simulation to stochastically interpolate data points with the goal of reproducing the patterns or texture of observations. And so instead of making one kind of best fit interpolation to the data, we generate hundreds of stochastic realizations. And that allows us to produce things that look much more realistic. We've also done some ice sheet modeling work and have found that when we model ice flow with simulated topography as opposed to the smooth topography that everyone uses, the ice behaves much more differently. There's a lot more deformation at the bed. We can see higher temperatures here. So this is showing us that if we use simulated topography, we can produce different ice flow behaviors. And this is really important for projecting sea level rise from ice sheet contributions. So what we want to do is produce simulations like this for all of the topography of Greenland. But this is a big computational burden because we have over 30 million data points here. Greenland is thousands of kilometers long and hundreds of kilometers across. So this problem is computationally expensive. And we are also calling this project Demogorgon Greenland for digital elevation models of geostatistical origin. I think Demogorgon is a Dungeons and Dragons reference, so my students have a lot of fun with that. But our goal is to create many realizations of the topography of Greenland and also create some sort of tools where users can run their own simulations. But this algorithm that we use to do simulations is extremely slow. And that's because most geostatistical simulation algorithms are sequential. So we fill in one point at a time, and that's really inefficient. So if you have some unknown topography with some black dots representing measurements, to simulate a point, what you do is you estimate the probability at a given location that you want to simulate and randomly sample from that distribution to create your simulated value. And you have to repeat that process over and over for every point. And we have found that the slowest step in this algorithm is the nearest neighbor search. The nearest neighbor search is when we have a grid cell we want to simulate, and there are other measurements of the bed nearby. We need to find what the nearest neighbors are so that we can use all of that information of nearby bed values to create a conditional distribution of what we think the bed elevation value is to get this probability here. And we can't just do a simple nearest neighbor search. We actually perform an octant search, which means we look for data in each octant. We're not necessarily finding the n closest neighbors. We want to make sure we're having data on every side of the grid cell we want to simulate. And that's important for creating a balanced simulation that's not too heavily skewed to a nearby flight line where there maybe is a lot of data nearby on one side, but we want to use information from all areas surrounding the grid cell of interest. So in order to do the simulation, we have to run through our array of 30 million data points and break it into octants and find the nearest neighbors within each octant. And after you simulate each grid cell, that gets added to the list. This nearest neighbor octant search becomes increasingly slow over the course of the algorithm. So that we found that that's the biggest bottleneck in our algorithm. So this is a profiling result for the simulation of a single grid cell. And in purple is the octant search. So there are 8 little purple chunks here for the search in each of the octants. So you can see that it's taking up a huge amount of the simulation time. So our goal is for the NVIDIA UF GPU hackathon was to parallelize this octant search and basically cut this time in 8 and parallelize it on a GPU. So our approach was to get our simulations running on Hypergator, the University of Florida supercomputer, profiling analysis, parallelize the octant search and make it 8 times faster, then adapt our simulation algorithm to GPU by changing some of the packages and rewriting other functions from non-GPU compatible packages in a GPU compatible format. So over the course of a few days, we were able to get a simulation algorithm running on a Hypergator on a GPU, and we implemented the parallelized octant search. We found that the simulation was actually slower for smaller areas when adapted to a GPU, but for really large data sets, such as the entirety of Greenland, we had a projected 30 times speed up for the full ice sheet. So the GPU version of the simulations is most effective for the large simulation areas. This was also my lab's first exposure to GPU computing and Hypergator and profiling. So it was a huge learning curve for us, and it was very helpful for getting us started and improving our familiarity with these concepts. One of the main challenges we had was that a lot of existing geostatistics, or all geostatistics packages in Python, are not GPU compatible, and many other packages like scikit were also not running on GPU. So we had to rewrite a lot of functions from scratch. There's still some that we need to get to if we want to be able to run it on GPU. We weren't able to get a final profile for our updated simulation algorithm, and I think it was because of some sort of like n-site versioning issue, also probably some user error, but that was also a challenge we were having. And then finally, because the simulation algorithm is sequential, there's kind of a ceiling to how fast we can make it, because the sequential algorithms are not very well suited for GPU computation. So some of our ongoing work is actually focused on reframing the sequential algorithm so that it can run mostly in parallel rather than one at a time. So what we're working on right now is we want to parallelize the nearest neighbor octant search for all of the grid cells, not just one. And we can do that before we even simulate a single point. So say you have a domain that you want to simulate and you have some blue dots that represent measurements. These numbers are a random simulation path. So this will be the first grid cell to be simulated, second grid cell, third grid cell, etc. And what we can do is we can actually calculate all of the nearest neighbors for each of these at the same time. And we can do that by saying, okay, here's grid cell 3. What we'll do is we'll calculate the nearest neighbor distances for all of the data points and all of the grid cells with a smaller number. So that way we're able to run a lot of the majority of the computational legwork in this algorithm simultaneously across the whole domain. So right now, a couple of my undergrads have written a parallelized version of the sequential simulation for CPU computation. So our next step is to adapt that to GPU. And we think that we'll be able to get 1,000 times speed up in our simulation algorithm. So yeah, right now it would take about 5,000 hours to run one simulation of all of Greenland on a CPU, about 200 hours on the GPU version. And we think it can, we can run them in less than an hour once we do this switch. So in summary, we've gone through kind of a long circuitous process of reworking our code and adapting it to GPU so that we can give the ice sheet modeling community these valuable topographic products for making sea level rise projections. And the NVIDIA hackathon was very helpful in getting us up to speed. So hopefully over the next year, we will be able to produce our final simulations. Thank you for having me.